Good evening, everyone. So, in the previous lecture, we discussed the Bayes estimates under the different loss function, where we have solved two questions in the class, and I asked you to solve other questions by your own. The solution was there, but I just hoping that you will solve them. Did you go through those questions? Anybody? Anybody of you tried those questions? Okay, so in those questions, in the first question, we just took the Poisson distribution as the our baseline, or you can say the experimental distribution, and the prior we can assume that it was the gamma distribution, all right, with the density function, right, and corresponding the posterior distribution was also the gamma distribution that we solved, and for that one we find out the estimates under the different loss function, under the self, under the absolute loss function, and line x loss function, and then precautionary loss function, and the entropy loss function. All right. So in that case, we just see the R coding. So what we do in that one, we are going to consider the first case here right now for the Poisson distribution as the experimental distribution and gamma as a prior. So we are doing a simulation study here. All right, in that one, we find out, we just took the true value of the theta as 3 and the alpha prior is 2 and the beta prior is 4. You are independent to choose the value of the hyperparameters as I told you earlier. So we are choosing because our posterior distribution is in the closed form, so we are able to choose the hyperparameters value uh, whatever we want. All right. So in that case, we are generating the first of all, we need to generate the random sample from the Poisson distribution. I hope you know how to generate the random sample in R for the Poisson distribution. Are you aware with that? Anybody? Okay. So for the Poisson, to generate the random number for from the Poisson distribution, we use the command poise for the Poisson distribution, and when we add the R before the command of the Poisson distribution, we are able to generate the random numbers of size n from the Poisson distribution with respect to the value of lambda that we are taking as a theta here. So now what we are going, and we are not going to change the random sample again and again, so that's why we are going to fix the random sample by the command set dot seed here. I hope you are able to see this one. Are you able to see our programming, the R window? Okay. So now we are going to generate the random sample from the Poisson distribution of size 25. Okay. So now this is our sample 562, 533, and so on. After that, we will take the sum of x, because if you just see here, in the estimates of the parameter, we have the summation xi, that is the sum of the random sample. All right, so that's why we are taking the sum of that one of random sample, that is 96. Now we are going to calculate the posterior parameters. So for the posterior parameters, it was alpha. that was alpha plus n, right? And for the beta, beta was beta plus summation xi, right? So in that condition, so we are going to take prior alpha prior plus n for the posterior density function. So the alpha for the posterior was 27 and the beta is beta prior plus sum of x, that then it will be 100, right? So now the Bayes estimates under the self loss function. So we are getting in the closed form. So we simply need to write down the formula of Bayes estimate of theta under the self, that was beta posterior divided by beta dash divided by alpha dash, that we are taking as the beta post divided by the alpha post here. So it will be, so Bayes estimates under self for sample size 25 is 3.70. That is not exactly 3.0 because the sample size is too small. If I am going to increase the sample size, say up to 50, so that time the Bayes estimate is right now 3.57. Okay, so now it is close to the true value. So again, we just try for the sample size 500. It is 2.93, means approximate to the 3. All right. If we just remove the set dot seed from the sample, so now the value is 2.91. All right. And the sample mean is 2.92 and Bayes estimates is 2.91. That means they are quite close, and that is they are nearby to the sample true value of the parameter, that is 3. All right. So this is the code under the self parameter. Okay, I will share all these codes with you. Uh, do you want to practice it right now or you want to practice it later? So accordingly, I will share the codes. Okay, I just do one thing. I just share these codes in the chat. Okay, so now all of you have the codes. So if you want, you can run it by your own on your laptops. Okay, this was the case simulation study case for the Poisson distribution. When X follows the Poisson distribution with prior gamma under the self. Now we just check the Poisson when the underestimation is more serious. So we are going to take the Linux loss function here. So whenever the line in the Linux you take the value of Q1 is greater than 0 at that time, we penalize the overestimation more than the underestimation. So here we are taking the sample size again 25. True parameter meter value of theta will be 3 and alpha prior is 2, beta prior is 4, and Q we are going to take as a 2. All right. This is the standard value of Q1, that is 2 for the when you are going to take overestimation more serious. Sometimes it's changed or based on your sample or your data that is given. So you can change the value of Q1. All right. So that's all on you. All right. So here again we are going to generate the samples from the Poisson distribution till here up to the posterior parameter. It will remain same, right? So Bayes estimate under the self, that is is the beta post divided by the alpha post, that it will remain same. Now what we are going to do, we are going to write down the Bayes estimate under the line x. So Bayes estimate under the line x is beta dash divided by the q1 log of 1 plus q1 divided by alpha 1. Alright, so we are going to use this one. So beta post divided by the q1 multiply by log 1 plus q1 divided by the alpha post. Alright, so we just simply need to keep the values of the alpha dash and beta dash here. Now we are going to run this entire code. Alright, so Bayes estimate under the cell is 3.70 and the Bayes estimates under the line x is 3.5729, means it is quite closer to the actual value of theta in compared to the self under the line x. Alright, so under the line x we are getting the more accurate value in compared to the self when we are taking the uh, gamma distribution as a self. Alright, let me check one thing. If we are going to use the increase the sample size up to 50, so it will be 3.57 now under the self, and under the line x it is 3.50, means still Bayes estimates under the line x is performing better than Bayes estimates under the self. Alright, if we just change the value of the alpha prior here, suppose we are going to put 6 alpha, we are not going to change the value of beta here. Let's see what will happen. Alright, still line x is performing better than in compared to self, because the parameters value is 3.32, that is quite far from 3, but the value of theta cap under the line x is 3.26. Alright, if we just increase this one up to say 10 beta prior, still it is performing better than the self, right? Because now right now the value is 3.42 and here value is 3.36, that is quite nearby to the q that one actual value of theta, right? So means that while changing the value of prior is not impacting that much. All right, so means line x is performing better, means when you are going to consider the situation when x follows the Poisson distribution and with gamma prior. All right, so line x means overestimation is more serious and providing the better results in compared to the when you are going to take the situation that where underestimation overestimation are both are equally serious. So in the condition overestimation, it will provide you the better results. Now we will check in the underestimation condition. All right, right now we are going to take the value of q1 is -2. Entire code will remain same, only the value of q1 will change. All right. Okay. So right now, if you just see one thing in your final results here, under the self, it is 3.70. Under the line x, that is 3.84, and under the precautionary, it is 3.72. Okay. It means that while you are going to take underestimation more serious in this study, that will not provide you the that much reliable results in compared to the self. Means self is better in compared to the line x. Okay, in compared to the line x, and under the situation of underestimation is more serious, the self is better, but self is not better than the precaution line x when you are going to take overestimation more serious. All right. So now we just try one more thing. We just increase the sample size up to 50, say 500, now 50. take the enough large. Okay, still it is not performing good. If we just take the sample size, say 50, at the time what we see what will happen. That is 3.57, 3.64, 3.58. All right. So right now you can do one thing. You have the code for the position and Bernoulli. So here you can change the value of the parameter of theta and you can change the value of the hyperparameters alpha and beta, and then you can try to check that in which combination of the parameters what kind of results you are getting. All right. So now we just take the another study for Bernoulli, right? So for the Bernoulli, we are taking the sample size of 10 and true parameter value of theta is 0.4 because in the Bernoulli, theta lies between 0 to 1. So we are taking 0.4 and the prior was beta distribution of first kind. So that's why we are taking the value of alpha and beta is equal, that is 2, 2. You can choose by your own. All right. And to generate the value from the Bernoulli distribution in R, so the command will remain same of the binomial distribution, but here instead of n that you usually provide, that is 5, 6, 10, you will take 1. So it will convert into the Bernoulli distribution. All right, so we just generate the value here and we check what we are getting. Okay, so 0, 1, 0, 1, 1, and so on, the values we are getting. Now we will take the sum of R, sum of X. So that is 4 because here, okay, Bernoulli, where is the parameters? The Bernoulli. Okay, so the prior of the Bernoulli was, sorry, what was the estimates of the distribution of the Bernoulli under that self? So under the self, it was alpha dash divided by the alpha dash plus beta dash. So right now, what was the alpha dash? Alpha dash was your alpha plus summation of xi. So that's why we are defining the alpha post, that is equals to the alpha prior plus sum of x, and beta posterior will be equals to the beta prior plus n, that is the length of x, minus sum of x, right? So we just find out what is the value of beta prior, beta posterior and alpha posterior. So that is 6, alpha post, beta post is 8. Now we will check what is the value of the Bayes estimate under the self. So it will be 0.42. All right, so the actual value is 4 and now the estimated value is 42. All right, so we will check all the results here. The sample proportion was 0.4, posterior alpha was 6 and 8, and true value of the theta was 0.4, and now right now it is 0.486. Now we just increase the sample size. So it is 0.4038. That is quite similar to the true value of the theta. Okay. So now we just try to change the value of the prior here, say 0.1 and 0.1, or you can say just remain it 2. Now we see what will be the impact. All right. So it's slightly changed when we are going to change the value of the prior. So if you just say we are not changing the sample, but we are changing the value of the prior, we are changing the value of the hyperparameters of the prior distribution from 2 to 0.1 and 2. So now it is providing the value estimated value is 0.39. So estimates value are changing based on your choice of the prior. So it will fluctuate. All right. Now we just check it again, say 2 and say it 0.2 of 2 to what is the still it is changing. All right, we are not changing the sample of the experimental data. So still by changing the value of the posterior hyperparameters, so it is estimated value is changing continuously. All right, so that's why the value of the hyperparameters is always very sensitive. So you need to choose the value of the hyperparameters very consciously. All right, so it should not fluctuate a lot. All right, so now we just check Bernoulli overestimation. All right, so if you just see here what we are doing, we are taking a sample size of 30. Parameters value is 0.4, alpha prior is 2, beta prior is 2. All right. So for the negative Q penalized underestimation here, so we are taking the value -3. All right. Sample generation will remain as it is. All right. And the posterior parameters will remain similar. Now come here. That is the important thing. If you just see here, you are seeing we are applying the for loop because what is the value of the Linux loss function means value of the theta cap under the Linux loss function. It was -1 upon q1, right? Minus q upon 1 upon q1, and then summation over the range of j, that is minus q1 raised to the power j divided by the factorial j into beta function. All right, for the beta function the command is beta here, that is alpha post plus j and beta posterior, right, divided by the beta alpha posterior and beta posterior, right. So right now we are breaking it is the infinite, because what is happening, you are writing factorial j here and it goes 0 to infinity, right. So when it will go 0 to infinity, at that time there is a limitation of r. Okay, there are the limitation of r, that it will not get the values of e raised to the power up to 200. More than that it cannot find out the observation. But if you will take a factorial greater than means that of 100, so at that time if we just see the factorial of 100, will it provide or not? Let me check it. All right, because it is up to 157, so it is providing. Now we check up to 200. All right, so it is providing the infinite. All right, so that's how I said it doesn't get the values more than e raised to the power 200. All right, so that's why we are running it up to the 100, because 100 is enough large. Even though in the summation, in the formula, it was summation up to infinity, but we will take up to 100 because it is enough large to estimate the parameter. All right, so that's why, because we need to take the sum, so that's why we are applying the for loop for that one. I hope you understand how we apply the for loop in R. Do you understand how to apply the for loop in R? Do you know? Anybody? Anybody knows how to apply the for loop in the R? Anybody is there? Or do I need to explain this one? How we apply the for loop here? All right. So what happened? Take the example here. Suppose I want to find out the summation of first 10 natural numbers. Okay. 1 to up to 10. I want to find out the sum in R. So for that one, what is the logical way to find out the sum? To find out the sum, it is first you need to start with 1, then you will add 1 to the next term, that is 1 plus 2. So that will be 3. All right. Now 3 is your output. Now you will add the 3 in the next term, that is 3, that will be 6. So 6 is your output. Then you will add the 6 in the next term, observation, that will be 10, and then 10 you will add in the next observation, that is 5, so it will be 15, and so on up to 10th. Correct? That's how we do the sum. Yes or no? Okay. So how you will do in the R? So you need to find out the value up to 10. All right. So what is the for the for loop? The command is for I in. Here is the variable. All right. Basically, what we are taking in. So starting point. All right. Semicolon. End point. Where you want to end the for loop, and in that one it will be expression. Okay. And close it. So that is your for loop. So now if I want to find out the sum from 1 to 10, what I need to do? I need to start with 0. All right. Because if I will add 1 here, so it will becomes 2. Then 2 plus 2 will becomes 4. So it will not provide you the correct answer. So I need to start with the 0. So suppose I am saying f is equals to 0, and then I need to start the for loop for I in. It should go 1 to 10, right? So that is the way to start the for loop. Now what I need to do, I need to introduce f here, okay, equals to f plus I. All right. And then I will close it, and I will get the, and I will call the f. You can try in your own laptop this one. So how it will work after this? So if you just see what I am doing here, I am doing first f should take the value 0 here, and 0 plus I should take the value 1. So it will go like this, f 0 plus 1, right? Then it should take the f should be equals to 1, and then it will go again. Now i's value will be 2, so f will be 1 plus 2. All right, instead of f it will be 1, and then I equals to 2, so 2, so it will be 3. Then now f is 3, so it will be 3 plus 3, so it will be 6, and so on. So that is the same procedure we are going to apply here. So what we are doing here, we are introducing a one term, that log term should start from the 0. All right, and here we are defining our summation term, that we are the posterior estimate under the line x we are defining here. In that one, it should not, we are using the if and break command. If it is providing the infinite, then it should be break. Okay, because we don't want infinite for our estimate. If it will provide infinite, so entire estimate will becomes infinite only. So that's why we are running it up to 100. So it should not provide infinite in that procedure. So that's why we are using this break command here in this one. So after that, log term sum that we are taking, it we will take equals to log term sum plus term that we are defined here. Okay, the same one as we discussed here. All right, and then after that, we call the estimate of that one. Okay, estimates under the line x, that is minus 1 upon q1 into this log of this term that we wrote here, log of this entire term. All right, and similarly for the under the precautionary loss function, we have the same one, that is square root of alpha dash plus 1 into alpha. All right, alpha dash into alpha dash plus 1 divided by alpha dash plus beta dash plus 1, then into alpha dash plus beta dash, and the square root of the entire expression. All right, so we will run this one. We will see what is happening. So under the self, the base estimate was 0.4706. Right now, it is 0.4813 under the line x, and under the precautionary, it is 0.4781. So under the precautionary, it is quite similar to the self, but under the line x, it is again not good enough in compared to the self. All right. So now what we will do, we will do the Bernoulli under the self. We didn't. We will do overestimation. It will remain same now. Instead of q1's value minus 3, we will take the plus 3, and now we will run it. All right. So q3, and for the value of q1 equals to 3, Bayes estimates under the line x is quite good in compared to the self. Means in the both examples, the overestimation is providing the better result in compared to the self or underestimation. All right. So now what we'll do, we just check the value. First, we just check on the large sample what is the final output. Yeah, still it is better than the self. All right. So your line x under the overestimation is providing better results in compared to the self. All right. So these were the codes for your both problems that I provided you. Now you will try the code for the other problems that I provided in the notes that you already have. Okay, you just try the code for other problems. Okay, so if you have any problem here, you can ask me. Otherwise, we can go ahead. Do you have any issue in this one till now? Anybody? Okay, so I just proceed. If you have any query or any doubt, you can ask me later. So now we will discuss about the Bayesian interval estimation. All right. So all of you, I hope, studied the confidence interval under the classical estimation theory. Did you study the confidence interval? Okay. So in that one, it is quite similar to that, but not exactly the confidence interval. All right. So in the Bayesian, we don't call it the confidence interval, we call it the credible intervals. All right. Why we call it as the credible intervals? Because we are not finding the confidence interval with respect to the experimental distribution. All right. In classical estimation theory, what you were doing, uh, you had the uh, distribution of your random sample or your experimental data. With respect to that, you used to find out the confidence interval of your parameters. But right now, here, what you need to do, you need to find out the posterior distribution with respect to the your parameters under study with experimental data, and then you need to find out the confidence interval of your posterior distribution where the prior information also involves. So that's why it is called as the credible intervals. All right. So the formula of the credible interval is basically the probability that theta will lie between ux curl and vx curl given that experimental data or the observations are provided at that time. You will find out the integral over the range of ux curl and vx curl of posterior distribution with respect to the parameter theta that should be equals to 1 minus alpha, that is usually we take as 0.95. All right. So but it is not always 0.95. You can change it according to your study, but most of the time people just take it as the standard one, but this is not the standard. Okay, just remember this thing. It is not a standard, but people assume that it is standard. So mostly we just take it as 0.95, that is 1 minus alpha. So when the interval u x curl to v x curl is an interval estimate of theta, in the sense that the conditional probability of theta belongs to the this interval is equals to 1 minus alpha. This interval often called as the credible intervals. So how we find out the credible intervals here? So suppose pi theta given x curve is your posterior distribution of theta. All right, and we are interested to find out the probability that the parameter theta should lie in the interval a to b. So at that time, you just find out the interval integral over the range of a to b of your posterior density function with respect to the theta when it is a continuous case. Otherwise, if it is a discrete case, so at that time, we just take the summation over the range of theta should be equals to a to b of your posterior PMF. All right. So this probability is the measure of the degree of the belief that theta belongs to A to B, given that the sample and the prior information or prior distribution. All right. So if you just first of all just remember that one, we are using the word prior information, not the prior distribution, because it is not necessary that prior should be always follow some distribution as we have seen in the Jeffrey prior and the non-informative prior. All right. So there is a one important thing that you should know. If the your posterior density function is a unimodal posterior distribution of theta, then your it is obtained that the posterior with the value of theta equals to a given x curve should be equals to the posterior distribution with the value of theta equals to b given x curve. that means it should be symmetric at that time. If it is a unimodal distribution, all right, the credible intervals is called as the highest posterior density interval. So this is the name of the confidence interval in the Bayesian, that is called as the highest posterior density interval. In the short form, we call it as the HPD interval. All right, so 100 into 1 minus alpha percent credible intervals for theta is an interval A to B such that probability that theta belongs to A to B given x curl should be greater than equals to 1 minus alpha if such an interval requires. There are two conditions when you call it as the we'll call it as the HPT interval. First of all, probability theta belongs to A to B given x curl should be equals to 1 minus alpha, and the second condition is that the posterior probability of theta is greater than that the any other interval for which assumption one holds, that is if A and B is an credible interval, then for any theta 1 belongs to A to B and theta 2 should not belong to the A to B. Means the probability of your density function, posterior density function should be greater than equals to, for any value of theta 1 should be greater than for the any value of theta, say theta 2. All right. So if this condition is going to be hold at that time, we call it the credible interval as the HPD interval. All right. Means there should not occur any other estimated value of theta. For that, the posterior density function has the maximum probability. All right. Posterior density function should have the maximum probability only for the one parameter estimated value, say theta 1 only. Are you getting this point? Anybody? Okay. I just explained it again. If you are not getting this point, we are saying that you know that how to find out the credible interval. Okay. How to find out the interval estimation. All right. For the posterior distribution, you just find out the value. You need to find out when you integrate over the range of A to B, your posterior density function, and then you find out the value of A and B. So that value of A and B will be called as your the credible interval or the range, or you can say the interval estimation of the parameter theta, right? But it is not the highest posterior density interval. See, if it is your posterior density is a unimodal, all right. If your okay, if your posterior density is a unimodal, suppose it is a normal distribution, so you will have the highest probability at the one place only. All right. So for that one, with respect to this highest probability, you will get the only one value of theta. All right. Say theta 1. There will any other value of theta will not occur at this point. All right. For any other value of theta, say theta 2, it will be less than the posterior density. All right. The probability of the posterior density will be less than in compared to theta 1 only. Yes or no? If I am saying it is a gamma distribution, so for the gamma distribution, it is like this, right? So the highest probability you are getting here. So here, there will be a single value of theta, right? Any other value of theta will not occur if it is a unimodal. Yes or no? Right? Whatever the value of theta will occur, right? Whatever the value of theta will occur, the probability will be smaller only. Either it will occur here or it will occur here. The probability will be less. So the same thing we are saying here. So for the value of theta 1 should be posterior density should be greater than for theta 1 in compared to the posterior density for the value of theta 2. Alright, whatever the value of theta you are going to take. So in that, when it happens, so it will call as the SPD interval. So usually we call it as the SPD. When we find out the confidence interval, it is always SPD interval only. Alright. So now there are 2 points that you should know. In the case of the posterior density function, posterior distribution is symmetric. We may construct the SPD credible interval a comma a plus h, where h is greater than 0, such that h is as small as the possible subject to the condition. That means if we find out the confidence interval here, not confidence, sorry, credible intervals through the this equation, probability theta belongs to a comma b given x curve equals to 1 minus alpha, then we have pi a plus h given x curl equals to the pi a given x curl. All right. If h is an arbitrary constant, so in that case also it will be equal. And if it is unimodal and symmetric, at that time a will be equals to minus b, as we have seen in the case of the normal distribution when you find out the credible interval, sorry, not credible, confidence interval for the normal distribution, right? The same thing we apply here. So now we will solve one question for the credible interval. So here we are assuming that x1, x2, xn be a random sample from the normal distribution with parameter theta comma 1, means mean is theta, variance is 1, and the prior distribution of theta is assumed to be non-informative, that is, we are considering g theta equals to 1, where theta lies between minus infinity to infinity. So now the question is construct the 95% SPD interval, okay, of theta and compare it with the classical confidence interval. So now we need to find out two things. We need to find out the 95% SPD credible interval of theta, and then we need to compare it with the classical confidence interval. Okay, so now come here. So the PDF of normal distribution with parameter theta 1 will be 1 upon root 2 pi into e raised to the power minus 1 by 2 x minus theta square, because sigma is 1. So sigma will not appear in the normal distribution. X will lie between minus infinity to infinity, and theta will also lie between minus infinity to infinity. After that, we will take the likelihood function of the experimental distribution. It will be 1 upon under the root 2 pi raised to the power n into e raised to the power summation I goes to 1 to n xi minus theta whole square. Now we will compute the posterior distribution with respect to the theta. So for that one, we have the formula, that is posterior distribution pi theta given x curl will be equals to the likelihood function of x curl given theta into the prior distribution divided by the integral of likelihood function into the prior distribution and integrated over the range of minus infinity to infinity. That means over the range of theta. All right. So now, because the prior distribution is 1, so at that time, we will simply write down the likelihood function 1 upon root 2 pi raised to the power n into e raised to the power summation I goes to 1 to n xi minus theta whole square, right, divided by into 1 divided by integral over the range of theta 1 upon root 2 pi, okay, raised to the power n into exp exponential e raised to the power summation I goes to 1 to n xi minus theta whole square into 1 d theta. So 1 upon root 2 pi raised to the power n is a constant value, so it will be cancelled out. So after that we will have only e raised to the power minus 1 by 2 summation I goes to 1 to n xi minus theta whole square. Same expression in the denominator and integrate over the range of minus infinity to infinity. Now what we will do, we will expand xi minus theta whole square, alright, and take the summation inside. So what we have summation I goes to 1 to n xi minus theta whole square. Alright, we just split the window. Okay, we have this expression. So now we are going to solve this one. Summation I goes to 1 to n. So it will be xi square plus theta square minus 2 xi theta. Right. Now take the summation inside the bracket. So it will be summation over the range of I xi whole square. When you will apply the summation on the theta square, so it will becomes n theta square minus 2 theta summation over the range of I xi. Correct. So summation xi can be written as, what is the formula of mean? X bar equals to 1 upon n summation over the range of I goes to 1 to n xi. So from this one we can write it as summation I goes to 1 to n xi equals to n x bar. Alright, so we use this relation and then we will have summation over the range of I xi square plus n theta square minus 2 theta n x bar. Alright, the same expression we will have in the denominator. Sorry, give me a second. So it is inside the exp minus 1 by 2, right? So now integral over the range of theta exp, and here you have one more bracket. So it is minus 1 by 2 summation over the range of I xi square plus and theta square minus 2 and x bar theta d theta. Alright, so now what we will do, we will multiply and divide, we will add and subtract n x bar square in the numerator and denominator both. So it will become exp exponential minus 1 by 2 summation over the range of I xi square plus and theta square minus 2 theta n x bar. Now add n x bar square minus n x bar square. Alright. Will it make any impact on the expression? Because it will cancel out, so it will be 0. So it will not make any impact on the expression. So similar thing we will do in the denominator. Integral over the range of theta e raised to the power minus 1 by 2 summation over the range of I xi square plus n theta square minus 2 theta nx bar plus nx bar whole square minus nx bar whole square d theta. Alright, now the summation of xi square is a constant or not? Summation xi square, is it constant or not? Tell me. Right, it is constant. So it will cancel out. Right. So now you have n theta square minus 2n theta x. Alright. And nx bar square and nx bar square. So nx bar square will also a constant or not here? Nx bar square will also a constant or not? It is also a constant. So we will, yes, so we will cancel out this. Okay. So now what you have? We have the remaining things is exponential minus 1 by 2 and we can take common, right? And theta square minus 2 theta x bar plus x bar square. Similarly, in the denominator, integral over the range of theta e raised to the power minus 1 by 2, take n common, theta square minus 2 theta x bar plus x bar whole square d theta, right? So it will be converted to your e raised to the power minus n by 2 theta minus x bar whole square, okay, divided by integral over the range of theta e raised to the power minus n by 2 theta minus x bar whole square d theta. Why is it a constant in the numerator if we are not integrating? Which one you are saying? I didn't get that one. See, what we are doing. See, yes, we are integrating here. When we are integrating in the, see, in the numerator, we have only likelihood and prior information. In the denominator, we are integrating over the range of theta, not over the, means we are over the range of xi. All right. So when we are integrating with respect to the theta, not with respect to xi. So xi will becomes your constant value because this is known one. This is not unknown. When you are finding the posterior distribution, so first of all, they provide you the values of x. So if you just see here in the formula of the posterior density, we are writing posterior pi theta given x curve. We are not writing pi theta comma x curve, or we are not writing theta x curve given theta. We are not writing these two things. Okay, we are writing theta given x curve means x curve or xi are known. Alright, when xi is known, so at that time it will becomes constant. Right, it will behave like a constant. So that's why we are writing, we are doing the integral over the range of theta. So how we can do it? You can take the exponential inside. All right, you can take the exponential inside. So at that time, if you just see here, you have exponential e raised to the power minus 1 by 2 summation over the range of I xi square and plus the remaining object, remaining things, right? Divided by integral over the range of theta ex e raised to the power minus 1 by 2 integral, summation over the range of I xi square plus the remaining things, right, with respect to theta. Because it is in the power, it is in the power of e, so can I write it as e raised to the power minus 1 by 2 summation over the range of I xi into e raised to the power minus 1 by 2 and this remaining thing here integral over the range of theta e raised to the power minus 1 by 2 summation xi over the range of I into e raised to the power minus 1 by 2 and the remaining thing d theta. Can I write it or not? Right. So if I'm writing this one and I am applying the integration over the range of theta, right? Over the range of theta, I am applying the integral, means with respect to theta. So e raised to the power minus 1 by 2 summation xi, can I write it outside the integral or not? May I write it outside the integral or not? Yes, if I can write it outside the integral, so at that time I can cancel out it or not. Okay, so this is the thing that we did. All right. So now, okay, so now we will solve it for further. Okay, so we had this expression, right? We have this expression. So now, what is the normal distribution? Normal distribution is 1 upon sigma under the root 2 pi e raised to the power minus 1 by 2 sigma square x minus mu whole square, right? If I integrate it over the range of x, that is minus infinity to infinity, it should be equals to 1. Correct? So if it is, I will put it equals to 1. So 1 upon sigma root 2 pi is a constant value. Correct? So it will, I can write it outside the integral. So at that time, it will be e raised to the power minus 1 by 2 sigma square x minus mu whole square should be equals to sigma root 2 pi. Yes or no? Right. Okay. So now what we will do, compare compare this expression with this one. So from here, your mu is equals to your x bar, right? And your sigma square is equals to your sigma square is equals to 1 upon n, right? So now it will be, this integral will be equals to, sorry, under the root 2 pi divided by under the root n. So now if you will write it like this, so at that time, because it is this part in the denominator here, this is in the denominator, so under the root n will go in the numerator and divided by root 2 pi. So this will again is your normal distribution with mean x bar and variance 1 upon n. Correct? Do you have any doubt till here? Do you have any doubt till here? Okay. So now we will proceed. Now we will find out the HP 95% HPD interval. So for the HPD interval, the formula was entry probability of theta should lie between A to B. Given x curl should be equal to 0.95. So what we will do, we will find out the integral over the range of A of your posterior density function and put it equals to 0.95. So posterior density we have under the root n divided by under the root 2 pi e raised to the power minus n by 2 theta minus x square d theta. So what we are going to do here, we will take under the root n theta minus x bar equals to z. So when you will find out the derivative with respect to theta and z, so by the chain rule of the derivative, so it will be under the root n d theta equals to dz, right? All of you have done this earlier, and we will put these values. All right, you have integral a to b under the root n divided by under the root 2 pi e raised to the power minus n by 2 theta minus x bar whole square d theta equals to 0.95. So we considered under the root n theta minus x bar equals to z. All right. From the chain rule of the derivatives, we find out the derivative of dz. So it will be under the root n d theta. It will be 0 because it's a constant. So it will be equals to dz. Right. Now put the value a and b instead of theta. So when you will put theta equals to a, so at that time it will becomes under the root n a minus x bar equals to z. So that will be the lower limit of z, And when you will put theta equals to b, so it will becomes under the root n b minus x bar equals to z. So that will be your upper limit of the integral, right? So similarly, we are getting here the upper limit and the lower limit. Then we will keep these values in the integral. So it will becomes integral under the root n a minus x bar and under the root n b minus x bar, right? Into under the root n divided by under the root 2 pi into e raised to the power minus 1 by 2, and we are taking the square of that one, so it will become z square. So dz, so from here it will be d theta will be equals to dz divided by square root of n, so it will be square divided by square root of n. Square root of n will be cancelled out. So now z here is following the normal distribution with parameter L0 to 1, right? So you have right now integral under the root n a minus x bar under the root n b minus x bar, right? 1 upon under the root 2 pi e raised to the power minus 1 by 2 z square dz. All right. So here, if you just see that this is the normal distribution, right? And normal distribution is symmetric. All right. So at that time you can write it as, and it is symmetric about 0. So at that time you can write it as integral minus infinity to root n a minus x bar. All right. 1 upon root 2 pi e raised to the power minus 1 by 2 z square dz equals to integral under the root n, so b minus x bar to infinity 1 by 2 pi square root of 2 pi into e raised to the power minus 1 by 2 z square dz should be equals to 0.025. Yes or no? That you understand or not? Are you understanding this point? Okay. So you know that the value, the probability for this one, when you have the probability of, if you just write it, that integral minus infinity to square root of n a minus x bar 1 upon root 2 pi into e raised to minus 1 by 2 z square dz will be equals to 0.025 when the value of z in the integral here is 1.96 from the table that you know that. I hope you all of you know this from the table, from the z table. Do you know this? Okay, if you know that, that's fine. So in that case, what we will do, we will keep both of them equals to a minus x bar equals to minus 1.96. All right, and under the root n b minus x bar equals to 1.96. All right, so from that you get the values of a and b, that is x bar minus 1.96 divided by under the root n, and value of b is x bar plus 1.96 divided by under the root of n. All right, so your HPD interval will be x bar 1.96 divided by square root of n, x bar plus 1.96 divided by square root of n, and the average width will be 2 into 1.96 divided by under the root n. All right, if you just see this one, this is similar to your confidence interval of the normal distribution, yes or no? Your right now your credible interval is equals to your confidence interval or not? This is the confidence interval. You have the similar confidence interval, right or not? Right. So this is happening because of the non-informative prior. All right. So since 95% classical confidence interval of theta is same as the SPD credible interval, in this case, thus we conclude that for the non-informative prior g theta equals to 1, the SPD credible interval is coincide with the classical confidence interval. That means the if you are taking the confidence interval, means sorry, the non-informative equals to 1, at that time it will remain that one. It will remain the confidence interval. Right now I just check. Okay, even though if you will change it non-informative, but if you will take the Jeffrey prior, we found out that was 1 upon sigma cube, right? That was our Jeffrey prior for normal distribution, if you remember. Yes or no? Jeffrey prior xi theta was the proportion to the 1 upon sigma square. All right. Here we were taking sigma was 1. In this example, we were taking the sigma is equals to 1. So that's why even though in the Jeffrey pi, it will not make the impact. But if you will change here, if you will take the value of g sigma here, anything, at that time, or Jeffrey pi, instead of 1, you will take any other thing, any other prior information or prior distribution you will take. At that time, SPD interval will not remain the your similar to your confidence interval. Okay. So now we have the another example. Okay, that is x1, x2, xn. We have random sample from normal distribution theta comma 1, same experimental distribution as we took in the previous example. The prior distribution of theta right now is your normal distribution with mean 0 and variance 1. All right. So now they are asking to compute the SPD interval. So how we will compute? See, till the likelihood, it will remain same. Now the prior density will be 1 upon root 2 pi e raised to the power minus theta square by 2. Right? Because we are taking mean 0. So theta minus hyperparameter mean value of the hyperparameter will be 0 and variance is 1. So it will be theta square by 2, kind of standard distribution, standard normal distribution somehow. So now we will find out the posterior density function. So formula, you already know what is the formula of the density posterior density function. So we will write the posterior, it will be 1 upon root 2 pi raised to the power n into e raised to the power minus 1 by 2 summation over the range of I xi minus theta whole square into 1 upon root 2 pi into e raised to the power minus theta square by 2, the same expression in the denominator over the range of theta, so it will be minus infinity to infinity So it will be minus 1 by, 1 upon root 2 pi raised to the power n into e raised to the power minus 1 upon 2 summation over the range of I xi minus theta whole square into 1 upon root 2 pi into e raised to the power minus theta square by 2 d theta. So 1 upon root 2 pi will cancel out, 1 upon root 2 pi raised to the power n will cancel out. So at that time you will have this remaining expression here. So now we will do the same thing again as we did earlier. We will we will expand it. Okay, we will expand the summation and the square term. So you note the summation, we will expand the square term. So it will be xi square plus n theta square minus 2nx bar theta plus theta square. We will add this minus 1 upon theta square into the same exponential term because the base is same. At that time minus 1 by 2 will take common, so it will take 1 minus 1 by 2 and theta square will become plus theta square. So it will be plus theta square here, right? Now then same thing in the denominator, same expression will remain in the denominator. So what we will have here, summation xi square will cancel out as I explained in the previous question. So you will have only and theta square plus theta square. So you will take theta square into 1 plus n plus 1 minus 2 theta nx bar. Right, this will be the your expression. Now after that what we will do here we are taking n plus 1 common from this one expression, so it will become theta square. So 2 theta n divided by n plus 1 x bar, right? Then what we will do, we will add and subtract n x bar divided by n plus 1 whole square minus n x bar divided by n plus 1 whole square in this term. Okay, are you getting this point? Okay, so same modification we will do in the denominator. So at that time what will happen? Minus nx bar divided by n plus 1 bar whole square will cancel out, and that time you will have theta minus nx bar. Okay, so this expression will be theta square. Okay, I'm just considering this expression inside the bracket. Theta square minus 2 theta x bar into n plus 1. All right, plus n x bar divided by n plus 1 whole square. So this is the formula of x minus a whole square. So we will take theta minus x bar n divided by n plus 1 whole square, right? So same thing we are going to use here. So now in the denominator you have integral over the range of theta e raised to the power minus n plus 1 by 2 theta minus nx bar divided by n plus 1 whole square d theta, right? Again compare it with the normal distribution. Compare with this expression. Again compare with this expression. So now your mean term is nx bar divided by n plus 1, right? So now your mean is nx bar divided by n plus 1, and what will be your variance? So it is n plus 1, right? So means your variance is now 1 upon n plus 1 is your variance. So again, it will follow the normal distribution with mean nx bar divided by n plus 1 and variance 1 upon n plus 1. Right? Till now, do you have any doubt in this case to find out the posterior distribution? Should I proceed? Okay. So now again we will use the same procedure that we used earlier. We will find out the posterior density function, the integral over the range of a to b of this prior density, and that should be put equals to 0.95. So the posterior density is square root of n plus 1 divided by root 2 pi e raised to the power minus n by n plus 1 by 2 theta minus nx bar plus 1 whole square. D theta should be equals to 0.95. Here what we will do, we will consider square root of n plus 1 theta minus nx bar divided by n plus 1 equals to z. All right. So when you will integrate, find out the derivative. So the derivative of d theta will remain d theta. So it will be root n plus 1 d theta. And this portion is a constant. So it will become 0 and then equals to dz. So d theta will be equals to dz divided by square root of n plus 1. Right. Now here you can find out the values of a and b for your with respect to the z. So it will be under the root n plus 1 a minus nx bar divided by n plus 1 and square root of n plus 1 b minus nx bar divided by n plus 1 and the 1 upon root 2 pi e raised to the power minus z square by 2. So again z will follow the normal distribution with 0 comma 1. Right, and it's a unimodal and symmetric. So similar to the previous question, we can write it as minus infinity to root n plus 1 a minus nx bar divided by n plus 1 1 upon root 2 pi e raised to the power minus z by 2 z square by 2 dz will be equals to the integral over the range of under the root n plus 1 b minus nx bar divided by n plus 1 up to infinity of 1 by root 2 pi raised to power minus z square by 2 dz, that is 0.025. So we will compute it, limit equals to minus 1.96 and equals to 1.96. So at that time we will get the values of a, that is nx bar divided by n plus 1 minus 1.96 divided by root 1 plus n plus 1. And for the b, the value is nx bar divided by n plus 1 plus 1.96 divided by square root of n plus 1. So that is your HPD interval, right? Right now, if you just see it, it is not similar to the confidence interval as we changed the prior to informative. Okay, we changed the prior from non-informative to informative, so your HPD interval has been changed, right? Is there any doubt in this one, or should I go for the next one? This one is different from the previous one. Should we proceed? Okay. Only you are responding. None of other people are not responding at all. Okay. So here we have a question. We are saying that x1, x2, xn be a random sample from the exponential distribution with parameter theta, and the prior density of theta is we are considering as the gamma. Okay, with parameter alpha and beta, now construct the 95% confidence interval. Okay, so the likelihood of the exponential distribution will be theta raised to the power n e raised to the power minus theta summation xi. I don't think you should have any problem in that one. And the density function of the prior distribution is alpha raised to the power beta, gamma beta, theta raised to the power beta minus 1 into e raised to the power minus alpha theta. Right. So now we find out the posterior density function here. So for the posterior density function, we write the likelihood of the exponential distribution, that is e raised theta raised to the power n e raised to the power minus theta summation xi into the density function of the gamma and divide by the integral over the range of theta, that is 0 to infinity, of your likelihood into prior. So now here alpha raised to the power beta and divided by gamma beta will cancel out from the numerator and denominator, and theta raised to the power n and theta raised to the power beta minus 1, we can add both of them, so it will become theta raised to the power n plus beta minus 1 and e raised to the power minus theta summation xi, and e raised to the power minus alpha theta can add because base is same, so it will become e raised to the power minus alpha plus summation xi. So now compare it with the gamma density, that is integral over the range of x alpha raised to the power beta gamma beta into e raised to the power minus alpha x into x raised to the power beta minus 1 dx should be equals to 1. So alpha raised to the power beta divided by gamma beta is a constant, so it will be x e raised to the power minus alpha x into x raised to the power beta minus 1 dx is equals to gamma beta divided by alpha raised to the power beta. Now compare both of them here, the denominator part with this one. So you have beta is equals to n plus beta and alpha is equals to alpha plus summation over the range of I xi. Right? So we keep it here. So it will become gamma function of alpha plus summation xi. Wait a second. Wait. So it is wrongly mentioned here. Okay, so your alpha dash is this is wrongly mentioned here. Okay, so your alpha dash is here alpha plus xi, sorry, alpha plus summation xi and beta dash is your beta plus n. Okay, so this is wrongly mentioned. Do not consider this one. Now we will so it's again a gamma distribution. Okay, so I wrongly mentioned here. Other than that, everything is fine. So it is for the confidence interval a to b, alpha dash raised to the power beta dash divided by gamma beta into theta raised to the power beta minus 1 into a raised to the power minus alpha dash theta, that is d theta equals to 1 minus alpha. Right. So now we are going to consider the PDF of the chi square. All right. What is the PDF of the chi square? Is 1 upon 2 raised to the power n by 2 gamma function of n by 2 into z raised to the power n by 2 minus 1 e raised to the power minus z by 2. Alright, so we are going to consider here the chi-square because it will convert into the chi-square. So what is happening? We are going to consider alpha dash theta. From here, alpha dash theta we are going to consider is equals to z by 2. Alright, so in that one, it will becomes alpha dash d theta equals to dz by 2. So d theta equals to dz 2 alpha dash, right? So now the limit will change, alright, because 2 alpha dash theta equals to z we considered. So it will becomes, when you will put a and b instead of theta, so it will becomes 2 alpha dash a equals to z and 2 alpha dash b equals to z. So now your integral will be integral 2 alpha dash a to 2 alpha dash b into alpha dash raised to the power beta dash divided by gamma beta. Now instead of theta raised to the power beta dash minus 1, it will becomes z by 2 alpha dash raised to the power beta dash minus 1 into e raised to the power minus z by 2 dz 2 alpha dash equals to 1 minus alpha, right? So now what we are going to do, you just consider, you just take 2 alpha dash raised to the power beta dash minus 1 and alpha dash together, so it will becomes 1 upon 2 and 2 also, so it will become 1 upon 2 raised to the power beta dash. All right, because minus 1 will cancel out with the plus 1. All right, so it will be 1 upon 2 raised to the power beta dash into gamma beta dash. All right, so alpha raised to the power beta dash will cancel out because alpha raised to the power beta dash and alpha raised to the power minus 1 will cancel out from this one. So it will becomes z raised to the power beta dash minus 1 e raised to the power minus z by 2 dz equals to 1 minus alpha. So now if we just see this one, so this is your chi-square density from here, right? Instead of n by 2, you have the beta. So your n by 2 is equals to your beta here. So it is, you have for, so now your z follows chi-square distribution with 2 beta dash degree of freedom, right? So means n equals to 2 beta dash. So degree of freedom is now 2 beta dash HPD credible interval. Okay. So now you need to understand one thing. Chi-square distribution is asymmetric, right? Chi-square distribution is asymmetric. So it is, you cannot write here alpha by 2, right? So that's why what we are doing, first we are going to consider 0 to 2 alpha dash a up to limit of the chi-square density function, that will be equals to alpha 1, okay, and integral 2 alpha dash b to infinity, we are going to do the integral of the this density function and we will keep it equals to alpha 2, and we are going to say alpha 1 dash alpha 1 and alpha 2 should be equals to the alpha, that is your 0.05, okay, or you can say 5%, right? So in that case, when you will keep it, so when 2 alpha dash a will follow the chi-square distribution with 2 beta dash with 1 minus alpha by 2, right? Because when you are going to do the entry, find out the confidence interval, so this part is always basically 1 minus alpha by 2 and this part is always alpha by 2, right? So we are going to say that 2 alpha dash a equals to chi-square will follow the chi-square distribution with degree of freedom 2 beta dash 1 minus alpha by 2 So A will be equals to chi square 2 beta dash 1 minus alpha by 2 divided by 2 alpha dash. And similarly, upper side, because it's upper limit, so it will become chi square distribution with with a degree of freedom 2 beta dash alpha by 2. All right, from the, because it is asymmetric, so B will be chi square 2 beta dash alpha by 2 divided by 2 alpha dash. All right, so now your credible interval will be 95% confidence. HPD credible interval will be chi square 2 beta dash at the value 0.975 divided by 2 alpha dash, and upper limit will be chi square 2 beta dash 0.025 divided by 2 alpha dash. So that will be your confidence interval, or not confidence, HPD credible interval for the exponential distribution, uh, for your experimental distribution, uh, exponential and posterior distribution gamma dash alpha dash. All right. So that is your credible interval. So again, we have the other question that is for the Gaussian distribution. I hope you will solve it by your own. Okay, so quick question. What is the difference between the symbol used for the prior in this example and the last one? Why it is G in the last question? G theta. Where? Give me a second. G theta. Where is we are using G theta? Where we are using G theta? The question this last. We are not using G theta anywhere. Where is G theta? Okay, first example of the non-informative. Wait a second. Let me check. Okay, see, this is the notation only. Sometimes we use J theta, sometimes we use G theta, sometimes we use P theta, all right, and other notations also. So these are the simply notation for the your prior distribution. Okay, these are the notations only. That is not going to make any impact. G theta is simply the notation for your prior distribution. Okay, yeah. Other things are same. That is not a problem at all. Okay, so other things uh, I have solved. I explained you three examples here. So now you have one example, and then you have another examples are there. So I hope you can solve these examples by your own. If you are not able to solve, then let me know. Up to here, then I will explain later. Okay, that is for today's class. I hope you will understand it, all these things. All right. If you are not, then let me know in the future. Okay. Goodbye for today's class. Thank you.